Greetings, everybody. This is Lazaros Moysis, and the topic today is chaotic maps to controllable statistical characteristics. So first of all, we are going to give you the motivation behind this work. Then we will discuss some solutions and approaches to this problem, and then end up with the things that we aim to do next. So the motivation behind our work is optimization algorithms. And in main optimization algorithms, there are specific actions like emigration, migration, selection, and mutation that are usually carried out in each iteration after a comparison with a random variable. Okay, so for example, let's say we have a random variable, and if it crosses threshold, we may have this sort of emigration, etc. action, or we may not have this action. So what we do here in chaos-based optimization, what we do is replace these random variables by a chaotic time series. And why do we do so? The idea behind that is to replace a random variable by a chaotic variable because, a random variable may yield a uniform distribution. So we have a sort of balance between how many migrations we perform and migrations, etc. But in a chaotic variable, we may not have that. So for example, in a recent paper, biogeography-based optimization using chaos, the authors find out that by using different chaotic maps, we may achieve different results and sometimes better results than using simply random variables, because chaotic time series and chaotic variables, they still possess statistical randomness properties, but they're also a bit more biased. And this may help in the performance of the algorithm. So that was our motivation to see whether we can construct chaotic maps that we can use in chaotic optimization algorithms that can have statistical desirable characteristics. So for example, whether we can go by choice from uniform to a non-uniform distribution, and how much non-uniformity can we control. So how can we achieve this? Many ways. Initially, what we considered is a standard piecewise chaotic map, the well-known tent map, which we generalized using three parameters, A, B, and C. And initially, what we did is study the effect of each parameter. So, in the symmetric case, we may achieve a uniform distribution of our chaotic values, but by affecting the value of A, we may achieve a skewness to the right of the distribution of values. And similarly, by changing beta, we can achieve this even better. So we may have an even higher non-uniformity, as you see right here, while by affecting C, we can actually affect and control what is the range of the values. So here it goes from 2.0 to 1. So, overall, we initially studied the effect of all of these parameters into the distribution of the chaotic time series. And we saw that we can generally choose appropriately the parameter values in order to achieve a desirable statistical characteristic. Of course, the map here shows chaotic behavior for a very wide range of parameters, as you see right here. But if we go to a color-coded version of this bifurcation diagram, you see that despite having chaos through and through, the value distribution changes. So, for example, as we increase beta here, you will see that this yellow region indicates that we have a more skewed amount of values yielding towards the number 1. So the distribution here is non-uniform throughout the bifurcation diagram. And you can see that using a graph. So here, for example, I'm increasing the parameter beta and computing the values of the matrix again and again. And you see that as I increase beta, actually I can manage to achieve this. The distribution of the values goes from being uniform to being non-uniform. And this is what we're trying to do actually, and we achieve this. Then, of course, if we look at it a bit more spherically by showing the double diagram indicating where do we have chaotic and non-chaotic regions for all the parameter pairs for A and B values, you see that we have a very wide chaotic region, and indeed inside this chaotic region, we managed to affect the mean value of the time series. So the mean value goes from 0.5 and up to 0.9. So we can effectively control the mean value, and a similar result holds for the variance. So overall, we can see that this map has a very nice property of being able to control its statistical characteristics. And of course, this is just an example of a piecewise map. There are many more maps in the literature. Here, as an example of a very recent work, they have a collection of piecewise maps. We see a different map right here, and another version right here, and another version of the piecewise map right here. And just as an example, we modify this map ourselves to control its left and right tip points, A and 1 minus A here. And again, we achieve the same results. Although we have a very wide region of chaos, we see that within this region, the values of the matrix are, of course, non-uniformly distributed. For lower values, they are closer to 0. For higher values of beta, we go closer to 1. So again, we can achieve this control of the distribution. We can go from uniform to non-uniform. Again, you can see right here, we start with a very skewed distribution. By changing the parameter beta, we go again to a bit more uniform distribution, but again, then a right skewed distribution. So the idea is that again here, by appropriately modifying the chaotic map, we can obtain a very good control of its statistical properties by changing the parameter values. So this is what we are actually trying to do, because we believe this will have a great effect in optimization algorithms. So we can control the parameter value to achieve a different result in our optimization algorithm. Again, by studying all of the chaotic region for all parameter pairs, we can see a similar result. The mean value can go from being very close to 0 to being very close to 1. So from left skewed to right skewed. So as a conclusion, our main contribution here is that we're trying to construct chaotic maps, piecewise chaotic maps, where we can actually control their statistical properties for the time series by appropriately changing the control parameters. So this seems to work very well. But as a future goal, although our analysis here is numerical, we also want to go, one step further and actually try to provide mathematical proofs about how we can control the parameters of the map to affect the mean value. And this is a very important result that we are trying to achieve. Of course, we tried 2 chaotic maps, but many different chaotic maps to consider from the literature. So we aim to extend our results even further to more chaotic maps in our study. And of course, finally, we need to apply those maps in chaos-based optimization algorithms. That's the last point. Of course, if we do all of these 3 goals, we are going to end up with a very high impact publication, I believe, because this is a very interesting topic. And if we achieve good results in chaos-based optimization, more and more authors are going to build and expand upon our own results. So, this is a very active area. So any contribution is going to likely get picked up by other research groups and get built upon and expanded upon. So, it's a very interesting area, a very active area, and we hope to contribute a lot more in the future. So these are all my main points. Thank you very much, and I'll see you all in the Q&A section.